Hello, this is Cynthia Challoner, editor of the Pharmaceutical Sciences Manufacturing and Marketplace Report, an exclusive feature of the new Pharmaceutical Technology Biopharm International Marketplace that covers technical, scientific, and market developments in the pharmaceutical industry. With me today is Svetlana Ivanova, Applications Development Manager of Air Products. She will be discussing the use of advanced cryogenic cooling technology in pharmaceutical synthesis applications. Could you tell us what is driving the development of novel cooling systems for use in pharmaceutical manufacturing and specifically for chemical API production?
Hi, Cynthia, and first of all, thank you for inviting me to talk about cooling processing and cooling methods. Answering your question, we believe there are two primary driving forces behind the need for novel cooling systems in the pharmaceutical industry. First is the need to achieve colder temperatures down to negative 60 degrees C and below, more economically and reliably. As we know, the use of such low temperatures is quite typical in the chemical manufacturing of API due to improved reaction selectivity, yield, higher API quality. The second driving force is the need to optimize the production of cycle times. As we know, batch processes are very common in the pharmaceutical industry. So enhanced cooling systems can help optimize the cycle times of the batch processes and reduce overall costs.
What types of automated liquid nitrogen-based systems then are available, and when would you use these different types of systems in chemical API manufacturing?
Selecting the appropriate liquid nitrogen-based cooling system depends on the specific of reaction. Air Products offer several reaction cooling systems, which we market under Polar Fit brand name. These liquid nitrogen-based systems can be supplied in different cooling capacities and can be used for both batch scale and continuous operations. Each Polar Fit system has cooling controls that are designed to prevent freezing or other process disruptions. Three major types of reactor cooling systems could be defined as direct, indirect, and semi-indirect. Of course, each method has its pros and cons. For example, direct injection of liquid nitrogen achieves a very fast response with high efficiency. Also, it's inexpensive to install, but some problems like foaming or localized freezing could occur, especially if system is not designed properly. This option is used often in emergency situations because vaporizing liquid nitrogen can provide rapid cooling to the reaction process in the case of unsafe or runaway situation. In semi-indirect cooling, the nitrogen is not contacting the reactor media. The cooling is provided by flowing liquid nitrogen through the coil inside of the reactor or outside jacket. Obviously, in this case, it's not as efficient heat transfer as indirect cooling, but it provides more accurate temperature control and is relatively simple in operation. Another liquid nitrogen-based system that I mentioned involves indirect cooling with heat transfer fluid. In these systems, liquid nitrogen cools down a suitable heat transfer fluid first in an external heat exchanger, and then the heat transfer fluid cools down the reactor through the circulation in the reactor jacket. This approach provides the most system flexibility, accurate temperature control, and accommodates different heat loads. Also, the nitrogen effluent gas in this case, just like in semi-indirect cooling method, could be reused as a plant utility gas. And as we know, most manufacturing sites have a use for clean nitrogen gas for purging and blanketing. The liquid nitrogen used in the indirect reaction cooling is not affected by the process other than being vaporized and warmed up slightly. So this gaseous nitrogen now can be further warmed and can be introduced into the factory network for use anywhere on the site, which could provide significant operating savings at the plant.
What would you say then are the advantages of using these three different types of liquid nitrogen-based cooling systems compared to conventional cooling methods?
We would typically compare a liquid nitrogen system to a more traditional system that is cooled by conventional mechanical refrigeration. And think very large home refrigerator, right? We believe the liquid nitrogen system has a number of advantages compared to traditional system. First of all, liquid nitrogen-based system can produce low-temperature refrigeration, typically think below negative 60 degrees C, more economically than traditional mechanical system, and I can explain why. Properly designed liquid nitrogen refrigeration systems can respond to load changes more quickly than traditional mechanical systems. This increases the potential for savings due to cycle time reduction. In addition, the economics of liquid nitrogen system are definitely tailored better for a multi-product batch-type plant. The cost of traditional refrigeration systems are fairly constant, whether they've been used or not. On the other hand, the operating cost of liquid nitrogen-based systems drop dramatically when the systems are not in use in the batch cycle. In addition, most, if not all, API manufacturing plants, as I mentioned before, have a nitrogen supply on site for inerting and purging or some other needs. For a modest cost, this nitrogen supply could be adapted to provide liquid nitrogen for refrigerating low-temperature reaction prior to its original gas usage. Also, liquid nitrogen-based cooling systems like Air Products Polar Fit could have, actually they do have, few moving parts and simple temperature controls, making the systems very reliable and easy to maintain compared to mechanical refrigeration.
So then what would you say are the latest advances in cryogenic cooling technology that's being used for chemical synthesis? And what do you see as being the remaining limitations, and what is Air Products doing to try and address them?
As I mentioned earlier, using heat transfer fluids-based cooling technologies provides the most flexibility, temperature control, and reliability. A big challenge for some of our customers is selecting a heat transfer fluid that is compatible with their existing operations and with the low temperature attainable with liquid nitrogen. When you are using liquid nitrogen to cool heat transfer fluids as low as negative 90 degrees C or even negative 120 degrees C, this represents a challenge because it's difficult to get many heat transfer fluids to operate at these temperatures. Such low temperatures could cause viscosity problems with many traditional heat transfer fluids. Also, many customers have concerns about freezing a heat transfer fluid with liquid nitrogen. In response to these challenges, Air Products built a reactor cooling evaluation system to help our customer to estimate the performance of different heat transfer fluids at lower operating temperatures in a pilot scale heat exchanger. For companies that are not ready to do experimental testing of a heat transfer fluid liquid nitrogen system for some reasons, Air Products can offer computational modeling that can help predict the cooling profile of reactor and behavior of heat transfer fluid under specific conditions without doing any experiments at the beginning. So this approach could provide the selection of the most appropriate heat transfer fluid system without doing any extensive lab or pilot testing. And I just wanted to mention that Air Products has more than 40 years of cryogenic application experience and has the know-how to help pharmaceutical companies identify the most efficient process cooling solution that would fit their specific application. Thank you.
Thank you, Svetlana. Again, this is Cynthia Challoner, editor of the Pharmaceutical Sciences Manufacturing and Marketplace Report. Been speaking with Svetlana Ivanova, Applications Development Manager of Air Products.